Welcome back, ladies and gentlemen, to some more physical science with Mr. Kenton. I'm going to keep moving us along here as we start talking about isotopes and our understanding of the structure of the atom. So we've been going through and learning how we can identify the number of protons, the number of neutrons, and the number of electrons in an atom. And so we're going to be able to use that information to help us better understand different types of atoms and some very specific terms that scientists use and that we're going to use to describe atoms. And so one of these specific terms that we have to describe are what are called isotopes. Now, if you recall, we talked about that atoms of the same element have the same number of protons. Like in order for something to be nitrogen, for example, it must have 7 protons, right? We established that earlier. But see, the thing is that not all atoms of nitrogen have the same number of neutrons. So as we can see here, we've talked about how atoms of the same element will always have the same number of protons, right? Our nitrogen example, all nitrogen atoms have 7 protons. That doesn't change. The thing that can change is that we know that some atoms are going to have different numbers of neutrons. So that means that there could be differing numbers of neutrons in the nuclei of different nitrogen atoms. Okay, so to define what an isotope is, it's atoms of the same element, so that means they have the same number of protons, but these atoms are going to differ or be different in the fact that they have a different number of neutrons. Okay, and maybe a comparison or an analogy that's going to make sense to us is going to come from some candy. All right, you can think of either Skittles or M&Ms here, right? So you've got different colored candies, whether we're talking about M&Ms or we're talking about Skittles, right? But they each have different colors. But at the end of the day, they're still M&Ms or they're still Skittles, whichever thing you're thinking of here. So the same thing is going to be true of our atoms. At their core, like if an atom has a certain number of protons, it's that atom at its core, it just changes in that number of neutrons. So think of it as like changing the flavor of the atom, like you change the flavor with an M&M or with a Skittle, okay? Now, what that means for us is that if it's an isotope, that means that the atoms have different mass numbers, right? Now, ultimately, what's the same, however, is that they have the same chemical properties, since the number of protons and electrons hasn't changed. And if you think back to the chemical properties that we learned about in the previous unit, electrons are really what determine the chemical properties of an atom. And so since those haven't changed, then the atom itself is still chemically the same, even though the number of neutrons has changed. So let's take a look at, here are some isotopes of the element neon. Now, I want to draw your attention here to a couple of things, right? You've been given the symbol notation for each of those 3 different isotopes. And again, I know that these are isotopes because every single one of them has 10 protons, right? So that means that they're all the same atom. But when we look at the number of neutrons, this one's got 10, this one has 11, and this one has 12. So it has the same number of protons, but it has a different number of neutrons. Okay, and as we can see here, each of them, not only do they have different numbers of neutrons, but when we look at the symbol notation, we see that each of them have different mass numbers. The first one has a mass number of 20, the second one has a mass number of 21, and the last one has a mass number of 22. Okay, and so what I want you to be able to take away from this when you look at this, that isotopes, they're all atoms of the same element. They have different mass numbers and a different number of neutrons. And as you can see with electrons, I didn't mention this, but they have the same number of electrons. That value didn't change in any way, shape, or form. Okay. Now, isotopes and average atomic mass. Now, if you remember, in the last video, at the beginning when we talked about mass number, I made a very big deal about the fact that mass number was not the same thing as average atomic mass. Okay, and so here I'm going to give us a connection to how mass number and average atomic mass are related to each other. So from the previous slide, we saw 3 different isotopes of neon, right? We had the isotope could be called neon 20, neon 21, and neon 22. Now, the thing is that each of those isotopes exist naturally in nature in very different amounts, okay? Now, when those amounts or abundances are considered, we are able to determine the average atomic mass of an element, okay? And so think of this average atomic mass like the percentage, going back to candy, right? Think about the percentage of red M&Ms or red Skittles in the bag. That would be the abundance of Skittles, red Skittles or red M&Ms in your bag. And so each of our isotopes have a specific number of times or amount that they occur in nature. Now, looking at the periodic table, if you find neon, you're going to see that its average atomic mass is 20.18 AMU, atomic mass units, on the periodic table. Okay. Now, so what is that 20.18 telling you and me? Well, since the average atomic mass is closest to the number 20, right, because 20.18 would round down to 20, that means that the isotope neon 20 is the most abundant form of neon that's found in nature. Now, please don't hear what I'm not saying. I'm not saying that neon 21 and neon 22 don't exist, but what I am saying is that they are found much less frequently than neon 20. Okay, so being able to look at the average atomic masses on the periodic table, that's going to give you an indication of which isotope of the element occurs most in nature. Okay. Now, to show you how they get these calculations, the next slide is going to have one worked out. And so if you look at boron 10 and boron 11, so it tells you you've got the 2 isotopes. It tells you that boron 10 is found 19% of the time. So let's assume that you had 100 isotopes of boron, 19 of them would be boron 10. And it has a mass of 10 AMU. Then you've got your second isotope, boron 11. It has an abundance of 81%. So if we're going back to our example of 100 boron isotopes, 81 of them would be boron 11. And it has a mass of 11 AMU. So in order to come up with the average atomic mass, they take the abundances and they're going to multiply them by the mass of that particular isotope. So for boron 10, our abundance is 0.190. We multiplied it by its mass, 10, which gave us 1.90. For boron 11, 0.810 times 11 gives us 8.91. If you add up both of those values, you find that that gives us 10.81 AMU. Now, if you look on the periodic table and you find boron, it's element number 5, you're going to see that boron has an average atomic mass of 10.81 AMU. And so this is showing us directly how AMU, or how the average atomic mass can be calculated from the masses and the abundances of these isotopes. Okay, hope that was helpful. Looking forward to seeing you guys again soon.